So, as I mentioned to you, evolution and speciation are painfully slow. Okay, but how slow is slow? So I wanted to look at what is the total length of time between a speciation event. How long does this actually take? Well, it depends. Some folks go with the idea that evolution happens as a result of punctuated equilibrium, meaning that things change pretty quickly, and when they do, when they have a need for change, it will happen fast, okay? But after that change, you'll see little change over the rest of their lifetime. And I'll show you what I mean. Other species seem to kind of constantly be in this flux state, this constant back and forth, gradual kind of change. And so what we see there is that to get to a speciation event, this would take much longer. All right. So my punctuated equilibrium at the top, this would refer to like our allopatric speciation we were looking at before. So this means that we've separated these species. It happened very quickly because of geographical separation or whatever, and they've stayed separated and they're going to remain separated. There's no chance for gene flow in between. It happens very quickly, and that's that. And then they maintain that over a long period of time. Gradualism looks at the idea that evolution is slow, and over time you're going to have minor changes as a result of your environment changing, and that's okay. That's how it works, okay, for these particular species. So you get little changes over time. Now, depending on the type of species, we can also pull in this idea of a morphological species concept, and I've told you before that morphology is what an organism looks like, structurally, skeletally, whatever. But what we want to think about is how you can tie this idea into other known events and processes for speciation. And typically we look at morphological species concepts when we talk about fossils, because we don't have living organisms to look at and study and look at their genetics. It can also be applied to asexual organisms, so organisms that are clone lines. This works really well. And other times when we just don't know whether or not these species are interbreeding, we can start to look at morphology. This doesn't fit well with today's molecular biology as well, but it does fit very strongly with classical systematics. So looking at the idea that these visible characteristics or traits are a way for us to classify things. We've looked at bone structures before. Homologous structures suggest that this similar bone structure arose and has been maintained, but over time the bone structures have been used for different purposes. So a gorilla is not flying with its arms, a bat is not climbing a lot with its wings, although if you've seen a bat go up a tree, it can climb fairly well for these wing structures. But the idea is they have common ancestry to them. They developed these structures once, but now they're using them for different purposes. The idea here is this brings us to something known as convergent evolution. So looking at two very different lines of evolution, but ending up in the same spot. So starting with two very distinct or different parental populations and very different species in many cases, and ending up at the same target goal of some sort of trait that is favorable for both. So look at my analogous structures here. So this is the opposite of homologous. Analogous structures go with convergent evolution, and look at the idea that they have two very distant relatives, okay? But their evolutionary line has brought them to the same point, to the same phenotype, because they both live in the same sorts of locations, okay? So my Leptopteran over here on the left used to live in grasslands, just like a horse. They are not closely related at all, even though they look similar. But why do they look similar? They look similar because their evolution and their environment in which they lived forced the phenotype selection, forced the allele frequencies in a direction that means that their forelimbs look the same to us now. Evolutionarily, they did not get to the same place, the same route, but they ended up at the same goal. This is the same as your eye and a squid eye. We'll talk about this camera eye development when we look at the animal kingdom, also known as convergent evolution. You have not been related to a squid for a very long time, but you have the same eye structures. We'll look at why. Okay? Why would these be analogous structures? Not homologous, analogous. I've got a bat wing, a bird wing, and an insect wing. Well, a bat's a mammal. An insect is an arthropod. Bird is a bird. Reptile descendant. All of these are different evolutionarily, but have ended up at the same goal. What's the goal here? Flying.